Okay, so good morning, everybody. It is a pleasure to have a guest speaker from France today. So a bright young researcher who's finishing her PhD, and we're talking about a theme that we already that we already covered in our seminar last year. So MPC in the head and how to build especially faster signatures from this paradigm. Okay, so thank you very much, Eliana. So the floor is yours.
Thank you for introduction. Good morning to everyone. My name is Eliana Carozza, and I'm a PhD student at IRIF, Université de Cité. Today, I will present one of my works that is entitled Faster Signature from MPC-in-the-Head. And this is a jointly work with Dongbai, Geoffrey Couteau, Damon Gourdazi, and Antoine Joux. So our primary goal was to address some pressing challenges in post-quantum digital signature. As you may know, the National Institute of Standard Technology has an ongoing post-quantum cryptography standardization protocol process that focus on the need to define new cryptographic primitives that are secure against quantum adversaries. So among these primitives, of course, digital signature play an important role because daily we use digital signature to ensure the authenticity and the integrity in every virtual system. So one assumption believed to be quantum resistant is the syndrome decoding problem. That is from everything okay?
Yeah, it's fine.
Yeah. Okay, no, because I don't see any more the room, so it's okay.
Okay.
No, it's okay. It's okay. It's okay. So this is part of the code-based cryptography, and we will use in particular its regular form. So it's considered a strong candidate in post-quantum cryptography due to its apparent hardness, even for quantum computers, and in the same time, his simplicity from an algebraic point of view, because all the equations are just linear equation. So our approach leveraged this assumption together with an advanced protocol that is the MPC-in-the-Head, that is well known for yielding compact and secure zero-knowledge proof of knowledge. So the two main contributions of this paper and so of this presentation are an efficient multi-instance puncturable pseudorandom function that is defined by using AAS that is really good for speed, and also it's secure enough to be used doing the MPC-in-the-Head protocol. So it will be used to generate a zero-knowledge proof of knowledge that later can be switched to a signature scheme using fiat-sharing protocol. So this is exactly what we will do here. And let's start by exploring the core concept that is the MPC-in-the-Head. So as I said, this is a protocol that allows us to obtain a honest verifier zero-knowledge proof of knowledge. And as the name can suggest, a multi-party computation normally involves multiple parties, and each of them is holding a private data. Anyway, in this context, we don't have the real parties. In fact, the multi-party computation is just in the prover's head. So now we have a prover that he has a witness, of course, and he decided to imagine in his head and different parties and to share the witness among these n parties. So he can compute the MPC protocol in his head and obtain what is called the parties view. That is the set of all the value that party can see. And so it can commit to all these views to interact with a verifier. The verifier then can pick a party among these n parties that has supposed to remain hidden. And then the prover has to open all parties' view but one. By open, I mean he has to reveal all parties' view but one. And now the verifier has to check then two things. The first one is that the output of the MPC protocol itself is a valid output. So the correctness holds. And also, it has to verify that the commitment that were sent at the beginning by the prover are consistent with the view that were open at the end by the prover. So what we described here is just a scheme that in fact is an honest verifier zero knowledge proof of knowledge. And the zero knowledge proof, the zero knowledge property, is guaranteed by the fact that an MPC protocol is secure even against n-1 corrupted parties. So this means that here, even when we reveal all parties' view but one, this doesn't give to the verifier enough information to recompute the witness. For this security, regarding the soundness, for example, of course, the prover can try to cheat, but the only possibility is that he cheats on the view of the party that the verifier chooses to remain hidden. So since we have n parties, this probability is of course 1 over n, and we can increase the security by just doing parallel repetition of this scheme. Regarding the efficiency of the protocol, of course, it depends on the underlying MPC protocol that is run in the prover's head. And so it depends, of course, on the number of parties we are playing with. So by carefully choosing the number of parties, we can balance between the security and the efficiency. And at the end, we can still obtain something that is a honest verifier zero knowledge proof of knowledge, and that is both secure and efficient. So starting from this, we can obtain a signature scheme by using the Fiat-Chani paradigm that I will explain later. So this is what we will do here. These are the main contribution, and let's see how we can handle the all but one party's view. So we said that the prover has to share between the n imaginary parties in his head the share of the witness and also of the preprocessing material. Of course, we need an efficient way to do this. And of course, we can share these values just as random values. So the prover can just send random values to all parties. Of course, as you can imagine, if all parties' view were just random, then the correctness of the protocol was not guaranteed anymore. And this is why, at the end, the prover just had an auxiliary material, a little auxiliary material to the last one party's data. And this correction ensures that collectively the parties' shares produce something that is a valid outcome. So now, even with opening n-1 out of n, we still have, from an outside point of view, that all these values, all these shares are random. Then when we want to use this technique to define something that will be used in a signature, we have to be really carefully, because of course we need to ensure security. So regarding the soundness, as I said before, we will need parallel repetition, but also we need to guarantee the unforgeability. And in particular, we need that when we reveal n-1 shares and decide to keep one share hidden, we must ensure that this hidden share remain masked properly, especially when we are using this in a signature, because you can imagine that an adversary can ask more queries to a singing oracles. So we need that this information is always masked, is always properly masked. And this is why we will use a puncturable pseudorandom function. So what is this? We have a pseudorandom function, f, and we have a master key for this function, okay, such that using the master key, we can compute the output of all the input, so old point, for the function f. But also, we have a punctured point. This point, the goal is to have something that allows the prover, of course, to compute all output. So the whole value for all the points on f. But for an outside point of view, for someone that is not the prover, we need that he will be able to recompute all the output except for the punctured point. How we can do this? We will define, using, of course, this master key and the point that we want to hide, what is called a punctured key. And what is the property of this punctured key? Of course, this is succinct. And also, when the prover will reveal this punctured key to someone else, for example, the verifier, he will be able to reconstruct all the output for all the point except for the punctured point P. And also, so what's happening in point P will be just pseudorandom. So it will just be indistinguishable from randomness. Why this is useful in our scenario? Because we can use this property to hide the data that is corresponding to the unopened party in the MPC-in-the-Head protocol. So, for example, if we define the punctured point to be exactly the hidden party's view, then we can use a puncturable pseudorandom function to obtain this system that is working exactly as we want. So we have to understand how we can define this punctured key, because this is exactly the thing that we need to send to the verifier. So to understand how we can define it, of course, we have to understand how we can first instantiate the PPRF. So a common way to do this is to use a GGM tree. The GGM tree construction is made by using a pseudorandom generator that is a length doubling pseudorandom generator. So we have an input of a length lambda, and we have an output of length 2 lambda. But this output can be seen as a pair of 2 elements, and each element has length lambda, of course. We can call them F0 and F1. Why this is useful? Because we can see this as something that is in a binary tree. And this F0 corresponds to the left child of a node, and F1 is the right child of a node. So, for example, if we start here with our input X, and we use the PRG, pseudorandom generator, so with F0, we will go in these nodes, and with F1, we will go in these nodes. now the two children can become themselves parents. And so we will use them in the pseudorandom generator. So by iteratively doing this call for the PRG, we can construct at each level all the nodes for the tree. And so we can arrive at the end of the tree, where we have n different leaves. So now you can see that, of course, if you know this starting point, I mean, what we call the seed or the root of the tree, then by starting with it and by going with the PRG, you can reconstruct all the leaves. But now, what's happened if we want to reveal all leaves but one? Suppose, for example, that we don't want to reveal this leaf. So we can imagine that this one is our punctured point. Then what is the punctured key? We need enough information such that everybody that knows this information can still obtain all the other leaves. How we can do it? For example, for this leaf, we can just reveal it. Okay, but for these two leaves, for example, we don't need to reveal them both. We can just reveal this node and then let the verifier or someone else that want to reconstruct it use the PRG to obtain these two leaves. And for these four, for example, we can just reveal this information and just use the pseudorandom generator to obtain this subtree. So the key idea, in fact, is just that each node can be seen as a seed itself for a subtree. And now this tree element in blue is what we call the copath of this leaf. So this means that for revealing n-1 leaves, we just have to reveal this information. And this, of course, reduces the communication, because to reveal n-1 leaves, n-1 leaves, we just have to reveal log n elements. That is exactly how many elements are revealing here. So, of course, you can imagine that the properties that the PPRF will have depends a lot on how the pseudorandom generator is instantiated. So, for example, a common way to generate this, to instantiate a pseudorandom generator, is by using the Davies-Meyer function, where the two children, the left children and the right children of each node at each level of the tree are computed by using pseudorandom random permutation. So, of course, if we are working in this environment, we need to prove security in the random permutation model. And a common way to instantiate them, these two permutations, P0 and P1, is by using a fixed K AAS. So this is really efficient because, as you may know, encrypting with AAS is efficient. It only takes 1.3 cycles per bit. So it's efficient. The problem is not this. The problem is it's not resistant against collision attack, because here we have our fixed key. So imagine in a signature, an adversary for a signature that can make more queries to the singing oracle. And then we have this fixed key AAS. Then it's easier to find a collision. So this is not at all secure. And to solve this problem, some strategies were proposed. The first one was, for some works, adding a salt to the AAS. So they used just a salted AAS. But the point is that they used it in a really non-specific way. They didn't specify precisely. And also, they didn't take in account this salt in the security model. So when doing the security proof, the salt just disappeared. They took for granted that the salt was there and stopped. The other method that was proposed to solve the collision problem was using a hash function to instantiate the two permutation. And of course, this is collision resistant because we are working with hash function. But the problem here is that this is really inefficient, up to 50 times lower than the AAS instantiation. So in fact, our aim is to keep the efficiency of AAS, but of course, we want to provide a proper security argument. How we will do it? By defining a multi-instance PPRF. So what is a multi-instance PPRF? We define formally a Q-tau multi-instance PPRF as a PPRF that can handles repeated usage across multiple signatures. What this means, we have two parameters. The first one, Q, is the number of queries that an adversary can ask to a singing oracle. And tau is the number of parallel repetition that we run within each signature to reduce the soundness error. So this means that our PPRF can handle two different signatures, and in each signature, we have tau parallel repetition. This is what we want to construct now. This is just the definition. Now let's see how we can obtain this. As you can guess, to describe the PPRF, we need first to describe how the PRG itself works. So how our pseudorandom generator works. Our pseudorandom generator is a salted pseudorandom generator. So in input, it will use also a salt. And the salt is a pair of two keys, K0 and K1. These two keys will be used to compute the right and the left child for each node in each level of the trees. So this means that for computing the left child, that is F0, we will use AAS with key K0. And to compute F1, we will use AAS with the key K1. So the point is that our salt, so these two keys for AAS, will be the same across all the trees for the tau repetition. Now, we can instantiate it, and we saw it that by using this construction of PRG, we can have a really good speed up, a significant speed up, because we can go somewhere between 12 times and 55 times faster than the state of the art for the hash-based, of course. So if we compare hash-based PPRF and AAS-based PPRF, we are really have a faster scheme. So now what we will do, we want to arrive to the final PPRF. And to do this, we will first prove that the PRG is indeed secure, because otherwise it's unuseful to use it. And later we will define the PPRF and prove that if the PRG is secure, then the PPRF is secure also. So let's see if the PRG is secure. We want to prove that our PRG is Q tau instance T epsilon secure PRG. What this means, let's define it by defining a game. So we have a simulator and we have an adversary. The simulator, of course, knows all the information that are mandatory to use the PRG. So to use the PRG. And now the simulator can just pick a random bit. And if this bit is equal to 0, sorry, then he will send the output of the PRG. So he will use the real information, that is the real key and the real point, to send it to the adversary. But otherwise, you will just send a random value. And as you can guess, the adversary will win the game if he can guess the bit. So now we can say that our PRG is Q tau instance T epsilon secure if the advantage of this adversary in this game, supposing that the adversary is running in time t, then this advantage is negligible. So in our paper, we prove that our PRG, this one that we define like this, is indeed secure, it has this security. And we prove it in the ideal cipher mode. I will not go in the detail of the proof because it uses a lot of technique. The most important one is the H coefficient technique, in which we have a coefficient that measures the deviation between the real scheme transcription distribution and the ideal model. And we prove that this coefficient is nearly 0. So once we prove that PRG is secure, then we can use this PRG to construct the PPRF. If you remember, as I said before, the PPRF is constructed as a tree. So of course, to have a tree, we need the root, the seed. And here it's our root, K. But also, after the seed, we need to expand it by using at each level PRG. But our PRG is a salted one. So this means that here, to start our PPRF, our tree, we don't need just the root of the tree, but also the salt that is needed for the PRG. And so, of course, you can imagine that if you have both the information, that is the root of the tree, and the PRG that allow, the salt that allow you to apply the PRG at each node, you will obtain the whole tree. Otherwise, if you have just the salt, you still need the salt. You always need the salt, because without the salt, you cannot apply the PRG. So if you have just the salt and the copath of a particular leaf, suppose this one, then you can obtain all the other leaves but this one. In the same way, exactly the same way I explained before, where you just consider this node as a seed itself for this subtree. And so this is exactly the definition of PPRF, exactly as before. It's just that now each PRG uses salt. And now we can define what this means for this PPRF to be secure. We do this through we define a game. So we have, again, a simulator. Here, the simulator has to have not only all the master key that are the seed of the tree, but also has to need all the information that are related to PRG, so all the salt. So now he will pick a random bit, and if bit is equal to 0, he will just send the output of the PPRF to the adversary. Otherwise, he will just send a random values. And again, you can imagine that the adversary will win the game if he can guess the bit. So now we say that our PPRF is a Q tau instance TD epsilon secure PPRF if the advantage of the adversary in this game, supposing that he's running in time t, is negligible. What we can observe is that if the PRG that we are using is Q tau instance T epsilon secure PRG, consistent with the definition that we just gave in the previous slide, then the PPRF itself is Q tau instance TD epsilon secure. Because you can see that we are just using the PRG. If the PRG is secure, we just use it for D time, for create D levels. And this is the new coefficient that it's here. So at the end, we will obtain a multi-instance PPRF that is secure. It's fast, of course, because in the PRG we are using AAS, not hash function. And also is secure against collision because we define it to be secure among Q queries for the signature, and in each signature we are using tau parallel iteration. So this is secure enough, and it can be used indeed by a prover to implement at the MPC-in-the-Head protocol. So exactly in the same way, he will construct the GGM tree using the PPRF, and he will just give the party that is chosen by the verifier to be hidden. He will just consider its views as the punctured point, the leaf that has to be hidden, and just reveal the copath. So here, the leaves are all the shares for all parties. So the share of the witness and the share of the preprocessing material. And so this is a correct way to instantiate a multi-part MPC-in-the-Head protocol that can be used, as we saw before, to instantiate a honest verifier zero-knowledge proof of knowledge. And now we will see how zero-knowledge proof of knowledge can be transformed in a signature scheme. And we will see it with our second contribution, that is a regular signal decoding based signature. So let's remember first, what is the regular signal decoding problem? So now we have a matrix H, and we have a vector that is a noise vector, and it's regular, and his Hamming weight is equal to W. So this means that he has a really particular structure. When you can consider the vector as a concatenation of block, and each block has Hamming weight equal to 1. So now we can compute the syndrome that is equal to H type X. And now the syndrome decoding problem claims that knowing given H and Y, it's hard, even for a quantum computer, to find X. So why we choose to work with this really particular type of structure that is the regular noise vector? As I said, you can imagine the vector as a concatenation of W blocks. Each blocks, of course, will have a length, that is block size, equal to the total length of the vector X, bk, divided by the number of blocks, that is W. And now our vector X, that is our witness, can be seen in this way, where we have each block. In each block, we have a length that is equal to the block size. And in each block, we only have one non-zero entry. But since we only have one non-zero entry, we can in fact record just the index of that known entry. So for each block here, instead of taking all the bytes, we can just take the index of the non-zero entry. And so we can compress our witness by obtaining a vector that is has not anymore length bk, but length w, because for each block we have one entry. One entry that is the index of the non-zero entry. And now this can be useful, of course, but now we have to pay attention, because when we want to share the witness between the parties in the prover heads, then the share has to be made not anymore over F2, because we are not anymore we don't have anymore this bit. We are working on a ring that is ZBS. So we have to pay attention during the share of the witness. But how we can do it? Let's see. So we have a regular noise vector that is a witness X, and we can choose as a preprocessing material a new regular noise vector R. This vector is sampled by random. So now, since they are both regular, we can compute for both of them the compressed vector, the one that I just described. What is the compressed vector? It's just the vector that takes the non-zero entry for each block. So now, if you can figure it, that the compressed vector of X, it just has W entry, and each entry is the position of the non-zero entry in the block. And the same is for R. So if we consider the difference between these two vectors, we just have the distance between the non-zero entry of our witness X and the non-zero entry of the random vector R in each block. So in fact, our witness X can be, it's just the random vector R, but shifted by Z. So R can be considered as a mask of our witness. And this can be useful in using it in MPC-in-the-Head protocol, because now parties can hold the share of the random vector R and also of the two compressed vectors for X and for R. And so they can compute all together the vector Z, reconstruct it, and later each of them can locally use the vector to shift their share of the vector R. So this can be used at the end of in the MPC-in-the-Head protocol, when the MPC protocol is run. But the problem here is when we add the preprocessing material, we have to pay attention, because before, when we had just the MPC protocol, then the prover was just able to cheat in the MPC, but now he also can cheat in the preprocessing material. So the verifier has to check that the prover will not cheat. So the verifier, you can just imagine that he says, okay, you have a preprocessing material, I'm happy for you, it's okay, but you can use it just after you shift it with a permutation that is chosen by me. So in fact, when the prover run the MPC between among all these parties in his head, he will not use just the random vector R, but to compute the real vector Z, he will use the permuted R, where this permutation pi is chosen by the verifier. So in the real exchange, in the real protocol, we have the prover, the verifier, we have the public information that are the matrix H and the syndrome Y, and of course the prover knows the witness. So he will imagine n parties in his head, and he will share all the information among these parties. Also, the compressed vector for the witness X and for the preprocessing material R. And it will commit it to the all this share to the verifier that will pick a random permutation to be used by the prover before using the preprocessing material in the execution of the MPC. So as I said before in the previous slide, the prover can use his preprocessing material R just after being permuted by this permutation. Now the prover can execute the MPC protocol and obtain all parties' view. So it will commit to this view to the verifier that will pick a party that has to be hidden, and the prover will reveal all parties' view but one. So now the verifier has to check. The first thing is that this scheme is correct, so that the equation here, syndrome decoding, the equation is still satisfied, and also it has to check that the commitments at the beginning are still consistent with all the views at the ending. So we prove in the paper that this structure, this 5-round zero-knowledge proof of knowledge, is indeed secure. And we prove it with, the proof is a really huge part of our paper, because it requires a lot of claim and lemma, and also a lot of combinatorial analysis. So I will not go in details, but if you really enjoy the pain of combinatorial computation, you can take a look. However, it's important to understand that here we are using to instantiate this MPC-in-the-Head protocol, we are using our PPRF that is AAS based, so it's really fast and it's secure against collision. So now, as you may know, there is a common way to switch from a 5-round zero-knowledge proof of knowledge to a signature, and it's the Fiat-Shamir paradigm that allow to switch from an interactive protocol to a non-interactive one. So now we just have one user and he wants to sign a message M. He will still do all the 5 steps of the 5-round zero-knowledge proof of knowledge, but the challenges that before were chosen by the verifier are now just computed as hash function of a value that is just obtained by the previous step, concatenated with the message that has to be signed. So at the end, he will obtain a signature. And the properties of this signature are related to the properties of the 5-round zero-knowledge proof. And so this is exactly what we did to obtain our signature. That here how we have all the result for our signature. So as you can see, we decide to run our scheme also by using the hash PPRF to see the difference between this hash PPRF and our AAS PPRF. So we didn't consider the other AAS PPRF because it was not secure. So we are just considering all the instantiation that can guarantee security against the collision attack. And so we have hash-based and AAS-based with our PPRF. So now you can see that the time is really, really better. You can see that it's really faster. even by using the same scheme, because this is our signature. But by just modifying the use of the hash with the AES, we have a really faster result. And we compared everything with a synchron decoding we had. That's a result from 2023. And so you can see that it's faster even here, even if we don't lose too much about the signature size. So this is the final result. And so at the end, in conclusion, we instantiate a new way to use a PPRF that is AES based, so it's really fast, and it still guarantees security. So it can be, in fact, used to create MPC-in-the-Head, and from this, you can switch to a zero-knowledge proof of knowledge, and later get via Shamir to a signature. And that's what we did, and we obtain a signature that is both efficient and secure. So looking forward, we can say that we can optimize more our PPRF, and also maybe we can try to apply our MPC-in-the-Head paradigm into other advantage signature. So that's it. Thank you for your attention. And if you have some question, I'm here.
Thank you, Eliana. So, are there any questions? Yes, Joux.
Have two questions to ask about. The first question is a short name for two terminology.
Sorry, I don't understand.
Can you speak up, maybe?
Okay.
Yeah.
Two questions to ask. The first question is about some terminology you use, like PRG, like PPRF. Can you give
Yes.
the name of those two short names?
The punctured pseudorandom function. Do you mean this?
PRG and PPRF.
PPRF.
Yes.
What's the question? I cannot hear.
Well, this is for payments. Is it function?
Yeah, it was punctured pseudorandom function.
No. I have maybe a question, and I also you were mentioning in the end that you're doing basically that you have a 5-round interactive protocol, right? That will transform into a non-interactive signature scheme. Isn't there some kind of attack that by Calais and the Zaverucha on such 5-round?
Yes. But we choose positively the parameters to be resistant against this attack. In fact, you can see that some specific here we have some specific parameters to be resistant against this attack.
Okay.
So I have thank you for your talk, Nina. So I have a question on this new assumption like this. It's probably not new, but you do use this property that in RSD, it looks like you define in a way that your secret has to be evenly distributed among small blocks. Is that one of the main property why you need that?
Why we need that?
Yeah. So what is the main purpose? So you need to divide it into smaller blocks of less whatever, but you need to have a 1 within each of the smaller block, right?
Yeah, but this is just the regular noise. I mean, regular vector. You can still divide it in blocks.
Yeah.
And each block has just 1 0 entry. Is the definition of regular, right?
Right. So it's a little bit more special than the general because it could be possible all the ones are concentrated towards
Yes,
one
yes.
end where you don't have any.
Yes, this is more special, and we decide to use this regular just to take advantage of this structure, because
Yeah.
now we can just compress the vector in this way.
I see. Okay.
Mhm.
Okay. Okay. Basically, your secret is somehow embedded over there in this pattern, right?
Yeah, exactly.
Oh, so do you know the security of this assumption compared to the standard syndrome decoding, or they are sort of similar?
I mean, it's just different. You cannot compare really the signature that are based on the syndrome decoding to the regular one. There are some other signature based on regular one, but they are just previous signature from me and Jafra. So we're just still using this.
Oh yeah, sorry. I mean the attacks. So is the attacks for RSD?
Oh yes. So in our previous paper that is mentioned here, we described a lot of possible attack for this one. We described a lot of possible attack, and we also instantiate a specific attack for this RSD. So by using approximated bird paradox, we created a new attack. We specified a new attack, and we choose all the parameters to be secure even against our attack.
Thank you.
You're
That's
welcome.
Another question? Okay, so with this, so let's thank Jana again. Thank you very much for the very informative talk.
Thank you.
Yeah.
Yeah, so we good luck on your defense. And,
Thank you.
hope to see you soon.
Thank you. Thank you so much for your invitation and for this opportunity. And I will use this opportunity to say, if everyone knows something about our open postdoc position, please let me know.
We will definitely.
Yeah. Thank you so much.
Thank you.
Thank you. Have a nice day.
Bye,
Bye.
Jana.
Bye.
Bye-bye.
Bye.